Hello students, in this video I will discuss some important theorems like Morera's theorem, Cauchy's inequality, and also we shall see the definition of entire function and also Liouville's theorem. So which is the part of syllabus of complex analysis, mathematics paper 3, BSc 6th semester, Karnataka University, Dharwad. So now we shall discuss those concepts, properties of integral theorems, so that we shall see that first one, Morera's theorem. As we know that the Cauchy's integral theorem, if fz is analytic within and on a closed contour C, then integration of f of z dz over the closed contour C is 0 then. So that in this Morera's theorem, which is the converse of Cauchy's integral theorem, so that the proof of this theorem, this is due to Morera, depends on the fact that the derivative on of an analytic function is itself analytic there. So what is the statement of this Morera's theorem? Because obviously which is the converse of Cauchy's integral theorem, suppose this integral of f of z dz is 0 and also this function is continuous in a domain D, and this integration of f of z dz equal to 0 for every closed contour C in the domain D, then that function is analytic within and on a closed contour C as well as within a D then. So now let us take z equal to a be a fixed point and z be a variable point in D, because see that let us C be a closed curve consisting of C1, which is an anti-clockwise direction, that is C1, and minus C2, it is clockwise direction. So then by using the Cauchy's integral theorem or Cauchy's fundamental theorem, or which is the consequences of Cauchy's integral theorems, so suppose we have two domains, that is one domain inside another domain, so that a integration of that is C1 and C2 here, so that the integration of f of z over C1 is obviously it is integration of f of z dz over C2 then. So now we need to prove that it is fz is analytic. So obviously it is derivative exists there. In order to prove that derivative definition, we shall take it as here. Let capital F of z is an integral function of f of t dt over z a to z there. A be a fixed point, that is a fixed point there, but z is a variable there, and it is what we are going to see that in order to make it as a definition of derivative, that because we are going to prove that f of z is analytic, it means what this capital F of z means what this is an integral function f of z over a to z there. A is a fixed point and z is a variable there, and then it's a neighborhood of z is z plus h there means what small variations in z. So what is this difference there? So it means what it is a to z plus h there, so that from fixed point to z plus h, that this integration f of t dt there. So then subtracting these two, we are making the definition of derivative there, so that the difference of these two, we get it that integration of f of t dt over a to z plus h minus integration of f of t over a to z there. Obviously by the properties of definite integral, it becomes it is what it is the z to a, it is a minus of that, minus plus, it is becomes a plus there, it is over z to a there. So then it is then it becomes that is the variations in z to z plus h, this integration there. So that is what we have, a to z plus h. It becomes by the properties of definite integral, it means it is z to z plus h there. So then it is integration of f of t dt over z to z plus h. So now we are dividing both sides by h. So then obviously it is what here. So then 1 over h into integration of f of t dt over z to z plus h. It means what? Only that integration over what is the integration from that z to z plus h there. So that is the in the integration over this z to z plus h, what happens that we are seeing that, and then taking a minus f of z on both sides there, and then we obviously this we can take it as that is the f of z h by h there, multiply and divide by h there, ultimately which becomes again 1 over h that, and then since fz is independent of t there, so then it is z to z plus h dt, this integration is always h there. So that results, obviously we can put it in this form. So then what is that? Then 1 over h I am taking outside, from the fact that z to z plus h over dt is h itself, as that I have used here. So that 1 over h I am taking outside, and z to z plus h and z to z plus h. So that f of t dt minus is f of z dt there. So then what is this here? Since it is what here, taking a modulus on both sides, and obviously it is what there, if you take individual modulus 1 over h, that modulus of h becomes, it is only h itself, and modulus of this f of t minus f of z there. Obviously since function is continuous, so that it is definitely this this magnitude of f of t minus f of z is less than epsilon, that I am taking. And as we know that integration of modulus of dt over z to z plus h is h itself, that is what there, and h gets cancelled each other, and then modulus of capital F of z plus h minus f of z divided by h minus f of z less than epsilon. That is what it is, the definitely it is continuity holds there. So then you take it as the limit form of this one, it is the limit of capital F of z plus h minus f of z over h as h approaches to 0 is f of z. So this is the definition of limit exists of this one, definitely it is a derivative there. So it is the definition of derivative capital F dash of z equal to f of z. Therefore f of z is analytic throughout in D there, or inside D there. This is what it is, the Cauchy's that is what, Morera's theorem, or Cauchy's converse part of the Cauchy's integral theorem. Now we shall see the Cauchy's inequality there. Suppose that a function f of z is analytic inside and on a positive oriented circle C, center at z equal to a and radius r in it, if m denoted the maximum value of modulus of f of z, because since function is bounded entire domain inside D there. So then it is the modulus of nth derivative of f at z equal to a, it is the center there. That should be less than or equal to n factorial into capital M divided by r power n, or else we can take it supposed to be, if you take a z equal to z naught, that is there. So that obviously that function, suppose the function is analytic on a closed contour C, that center of the circle at z equal to z naught and radius r in it, and function is bounded, that is the definition of, then that is what that is modulus of f of modulus of nth derivative of f at z equal to z naught, that's obviously n factorial to capital M divided by r power n. So by making use of the Cauchy's integral formula for derivative, we have that. So this is the Cauchy's integral formula for derivative there. Take a modulus on both sides, and then we can take the individual modulus or magnitude of that. Since function is bounded, so that is what less than equal to m, and this is the equation of the circle, that is with the radius r there, and remaining, that is the integration of modulus of dz over c, that is it is the equal to 2 pi r, it is circumference of the circle. By making use of all these concepts, so that obviously it is a modulus of I is 1, so that it is a modulus of f of z is less than or equal to m, and this is what 1 over z minus a power z plus 1, it is a 1 over r power n plus 1. So this obviously it is 2 pi r, so then it is this integration of modulus of dz over closed contour C, it is circumference of the circle, that is 2 pi r, so that 2 pi 2 pi cancels each other, and then we have get this modulus of nth derivative of the function at z equal to a, where a is the center of the circle, that should be less than or equal to n factorial into m by Rn. This Cauchy's inequality is also called an immediate consequences of Cauchy's integral formula for nth derivative. We shall remark on this here. Suppose if you take as r approaches to infinity, this nth derivative of the function at z equal to a, it obviously becomes a 0. This Cauchy's inequality can be used to show that it is the entire function except at a constant is bounded in the complex plane. Now we shall see the definition of the entire function. A function which is analytic everywhere in the complex plane is called entire function. Means what? Function is analytic inside everywhere in the complex plane, which is the entire function. For examples, that all polynomials and transcendental functions are entire functions. So transcendental functions, it means, as we know, that there is a logarithmic, trigonometric and exponential functions. All are entire functions there. Now we shall, based on this definition there, we shall see the theorem here, Liouville's theorem. So statement of this Liouville's theorem: if a function f of z is analytic for all finite values of z and it is bounded, then this function is constant. That means a bounded entire function is constant. So then, which is what, suppose if you take a 2 z1, we shall see the proof of this by taking, that is the 2 arbitrary z1 and z2 be 2 arbitrary points of z plane. This z1 and z2 be 2 points in the arbitrary plane there, and choose the contour C to be very large circle of radius r, center at the origin, then and radius r units, and which containing points z1 and z2 we have chosen there, and such that obviously that modulus of z1 is less than radius r, and this modulus of z2 is also less than r there. Obviously that. Also, since function is bounded, there exists a real number capital M, it is a positive real number, such that this is the definition of modulus of f of z less than or equal to capital N for all z there. So by making use of that Cauchy's integral formula, we have taken, that is over the point that is at z equal to z1 and z equal to z2, we can take subtracting these two here. So that is what we are taking that, and simplifying this expression, that is what here. And z1 and z2, since those two are constant there, it is just cancels each other, and then obviously, which is what it is, this expression remains there. That is what this expression f of z over z minus z1 and z minus. So then we take the modulus on both sides and take the individual modulus, and obviously that since z minus z naught equal to r into e to the power of I theta, so it is this circle equation of the circle in the polar form, and then obviously it is. So then what it is modulus of z1 minus z minus z1, it is a capital R, and it is also capital R, and then it is by taking R, it's outside, and then obviously we get it, that is the what there, and it is the equation of the it is the integration of modulus of d theta over 0 to 2 pi, that is the 2 pi only there, and then make use of that, then obviously that is this one. And because since r contains in the denominator of this expression, as r approaches to infinity here, this terms becomes a 0 there. So then this difference, modulus of f of z minus f of z2, it is equal to 0. then obviously it is what that is there.